we've got two basic concepts. The first one is called interference. Interference is when two waves or more end up in the same medium, right? Which means that they interfere with each other. That's why it's called interference. When they interfere, the medium undergoes a change in amplitude equal to the sum of each wave's amplitude combined. You have to keep in mind that waves are energy, right? So the energy of these two waves is propagating through the medium because of a disturbance or a vibration that was created prior to. I've given two very distinct shapes so that you can clearly see this, right? Your waves were much more curved, right, when you were doing the spring, but it is possible to generate waves that look more like triangles and squares. Because waves are energy, they are traveling through the medium. So you see two wave pulses here, right? Two wave pulses. As they travel through the medium, right, they move the spring, the rope, whatever it is, away from the equilibrium position. We call that amplitude. On the left-hand side, we've got two that have what I'll call positive amplitude, right? And on the right-hand side, we have one that has a negative amplitude and one that has a positive amplitude. When they travel through the medium, at the exact moment when they overlap, right, they create a change in amplitude equal to the sum of each of the amplitudes of the individual waves. So what that means is that as these two are traveling together, at the exact moment when they overlap, since this one is a positive displacement in the shape of a triangle, and this one is a positive displacement in the shape of a square, they add together to create a shape that would be a square on top of a triangle or a triangle on top of a square, however you want to think about it. Well, waves are energy, and energy cannot be created or destroyed. And so what happens is that after they overlap, they return to their original state. Right? The energy does not change. They do not bounce off of each other, which a number of people start to think that in the lab. Right? When each of you are at either end sending wave pulses down, many groups observed that the waves hit and bounced off. That is not what happens. They in fact go through each other and come out the other side. Right? And that's why I've given you distinct shapes so that we can see that. So we're going to be looking at before, during, and after in terms of motion. So in the before case, the two waves were created independently on either side. They are traveling through the spring from one side to the other. At the exact moment when they overlap, if they are both on the same side of the equilibrium, then they constructive interference, they construct an amplitude that is greater than either one individually. Right? So they add together. After they overlap, they continue in their original state. So the triangle on the left is moving to the right. The triangle is now on the right, continuing to move to the right. The square is on the right, moving to the left. After they overlap, the square is on the left, moving to the left. Right? They literally pass through each other without being affected.
One of them is negative.
In this one, both of them are positive.
Okay.
In the destructive form of interference, we would call one positive and one negative, depending on which side we decide the equilibrium is positive and negative, right? In this case, if we're saying going up the board is positive, then the square wave has a positive amplitude. The triangle has a negative amplitude, so when they overlap, the triangle is going to subtract from the square, right? So that's what we see here is a pattern where if you were to lay the two on top of each other, right, the positive value gets canceled out by the negative value. You can imagine that if these two waves were exactly the same, right, except that one was positive and one was negative, at the exact moment of overlap, what would the rope look like? This was what you were doing in your lab. You generated one wave on one side, one wave on the other side. If those two waves are the same at the exact moment of overlap, what did you observe?
They cancel each other out.
They cancel each other out, and so the rope actually looks completely flat. Right? But the reality is that it doesn't stay completely flat. It's only temporary because the energy doesn't actually get destroyed. So it's unfortunate this is called a destructive because energy is not being destroyed. The amplitude is being destroyed. Right? After they pass through each other, they continue on in their original state. So the triangle that was underneath the equilibrium continues to the right. The square that was above the equilibrium continues to the left. Okay, so what I am looking at is I'm thinking about the equilibrium as being the state of the spring, rope, whatever it is, right, with no energy in it. When the waves are in the spring, they are displacing the medium a set distance away from the equilibrium position. We call one direction positive and one direction negative. It doesn't matter which one, right? When they overlap, because one is already moving the spring this far, and this one is already moving the spring this far, when they are in the spring on top of each other, they have to move it twice as far because one is moving it an amplitude away and the second one is moving it additionally. Does that make sense? This is why we call it constructive interference, because they are literally adding together during that time. The destructive, of course, is the other way around, right? Because one is positive and one is negative, when they combine, they subtract, right? And they become an amplitude that is actually less than either of them.
Okay. Wait, what?
Well, the amplitude of this,
okay.
in terms of absolute value, they become less, right? This one was, let's say, 5, and this one is positive 5. When they add together, they cancel out a good deal, right? With individual wave pulses, right, it's pretty simple to understand what's going on, right? Because we can actually observe this happening, which is exactly what you're doing in the lab. You are watching these waves interact in the medium together. Part 5 of the lab is a continuous wave input, right? Continuous wave input is when we're vibrating. If you go back and look at your notes, we had a picture of a wave pulse, and then we had a picture of a continuous input wave. Continuous input wave, you are continually adding wave pulses to the medium, right? And so you're vibrating the spring, the wave pulses are ascending down, reflecting off the end, reflecting back and bouncing back and forth. So you end up with many, 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 many waves all bouncing around inside the medium. Since there are many waves, you get a sizable amount of constructive and destructive interference going on, and you get really crazy looking patterns. However, if the continuous wave is input where the interference occurs in the same places throughout the medium, right, then you get what's called a standing wave. A standing wave looks like it's standing still. That's why it's called a standing wave, right? These, you can clearly see the energy, the wave pulse traveling, propagating through the system. In a standing wave, you can't. All you see is the spring bouncing up and down, but you can't actually see the translational movement.
Yeah, that can only happen in a spring, right?
Well, it doesn't only happen in a spring, but the spring is a very good example for visualizing what's happening. But actually, all waves, any type of wave, can actually create a standing wave. And we're going to look at a couple examples right now, and we'll talk about a few more next week. What's very useful about this is that standing waves don't always happen. The conditions have to be just right. That condition is waves with lambda divided by 2, right? That's a 2, not a z. Lambda over 2 factors of the medium's length will become standing waves. So I've given you the first 2 standing waves here on the right-hand side.
That's always the equation?
Yes.
how
So
many-
if I have a spring that is this long, and I shake it with just the right frequency, right? This is what you had to figure out in the lab. And if you haven't gotten to this, you will on Monday. If I shake it just right, I can get a pattern where it looks like a jump rope, right? It literally looks like a jump rope. So the spring is bouncing up and down and up and down and up and down. What you have to remember is that every input from you shaking the spring is actually sending a wave pulse down through the spring, which is hitting the end, bouncing off of the end, and traveling back this way. Right? They're actually vibrating back and forth through the whole system. All right, so in this case, right, the length is going to be the length between the endpoints of the spring. So it's literally how long it is. This is what you measured for your original length of your spring, right? When I vibrate it at a low frequency, I can get a nice standing wave pattern of what we're referring to as one hump, right? But really what this is one giant constructive interference pattern, right? The amplitude is maximized in the same place the whole time, right? Instead of it being a temporary display, right? You remember when we sent 2 wave pulses down, in the middle it flopped up larger than either wave, but then it leveled back out because the waves continue and separate apart. But if I'm sending many, many, many waves through there, right? If they're always meeting in the same place, which in this case is in the middle, right? Then they're exactly adding constructive interference in exactly the same spot every single time. And so what ends up happening is that the spring looks like the waves are not propagating, but instead just the spring is vibrating. But this is not actually true. The waves are vibrating down through the system, propagating along the length. You just can't see it. Using this knowledge, the star, we can set up this formula. L is lambda over 2 times n, where n is an integer factor of the number of standing waves. In other words, the first standing wave has 1 hump, n is 1. The second standing wave has 2 humps, n is 2. This allows you to calculate the wavelength of any standing wave. And it also goes back to understanding what a complete cycle is. Right? A complete cycle is all the way up, all the way down, back to its original position. This is one wavelength. Right? And that's where we're getting the idea from. A complete cycle is all the way up, all the way down, back to the middle. So the second standing wave has a wavelength that is the length of the thing between you two, right? This is because the spring is vibrating all the way up, all the way down, back to the original.
Yeah.
So this is one cycle.
Okay.
So if I go back and look at this one, this is all the way up back to the middle, that's only half. It's only half a cycle. So this is only half the wavelength. That's why lambda over 2. We need to be able to pick out this pattern and identify that as one wavelength.
So they equal the same thing? L?
No, they don't. Well, L equals the same thing because that's the length between here and here, right? The length of the spring. But that means that here I'm shaking slow, and here I'm shaking twice as fast because I'm getting twice as many vibrations.
Wait, but then why is it say lambda equals
Right, so I'm using this formula and plugging in the number of humps, which is the number of standing wave, to calculate lambda. So L equals 1 times lambda divided by 2. So I multiply by 2, and lambda is 2L.
Oh, I kind of get
Right? The wavelength of the first standing wave is twice as long as the length of the spring.
it. Okay.
This is because it's possible to get a standing wave that's only half a wavelength. The second wavelength, right, the second standing wave, because there are 2 constructive interference locations, right, or humps as we're referring to them, then n is 2. So I'm plugging in that n is 2, the 2's cancel, and wavelength is the length. Right? This proves that for the second standing wave, the length is the wavelength. That make sense? So then obviously you can go on from there, n equals 3, n equals 4, and so on. What's useful to think about is that if I plug this information into our formulas that we had from before, right? V equals lambda f. Then I can generate this set of equations, right? V equals lambda f. V equals lambda f. All I did is divide by lambda, right? And then I'm putting in that lambda, right, is 2 times L divided by n. 2 times L divided by n has an inverse because it's in the denominator. This is a formula for calculating the frequency of any standing wave, where n is 1, 2, 3, 4, and so on. The only thing you're going to change with the frequency is n, which is the number of peaks and valleys that you see going across the standing wave. N will always be an integer, and it will be very easy to count because you just look at the image, right? And if you have a standing wave with one hump, n is 1, two humps, n is 2, and so on. What's neat about that is that if we go through the math, which I'm not going to bore you with, the frequency of the first wave, right, has a wavelength that is half the length. We just went over 2 problems in the homework. If I increase the frequency, what happens to the wavelength? If I increase how fast I'm shaking it, what happens to the wavelength?
It gets shorter.
It gets shorter, which is exactly what's happening here. The wavelength of this wave is really twice as long as L, right? The wavelength of this wave is L, which is half as long. So the faster I shake it, the shorter the wavelength, and it scales perfectly inverse, right? Which means that if I double the frequency, I half the wavelength, which is really useful because if I can calculate F1, the frequency of the first wavelength, then 2 times that is the frequency of the second wave, and 3 times that is the frequency of the third wave, and so on and so on and so on.